Thanks so much, Darby, and everyone for joining the seminar. It's wonderful to have this, I guess, remote format, and of course it'll be always nice to go back in person, but we'll do this some other time. Okay, so let me share my screen. Just 1 second. Okay, does it come through well? Okay, so please, if you have questions anytime during my talk, please, I mean, raise your hands. I won't be able to see it, but just raise your voice. Just unmute yourself and ask questions. So I'm happy to answer questions anytime during the talk here. So, and I'm very much privileged to be here at the COINFLIPS series, and for many years, stochastic computing or stochastic modeling in neuroscience has been very much at the core of what we do in neuromorphic computing. And I still remember Carver Mead, who started the field of neuromorphic engineering, challenging us. This was 20 or 30 years ago. Can't you actually have those neural systems in silicon take advantage of the noise, the physical noise that's naturally present there, to actually, rather than fighting it, which you normally do, trying to get a high SNR, signal-noise ratio, why don't you take advantage of the noise as a mechanism for doing learning or other means for correlating signals, and sure, that got us all started, and so I'm very glad that there is some great interest in that also at Sandia and other a community of researchers that care about this. Yeah. Okay, so that's the setting. So we'll talk about efficiency and resilience. And so resilience has two sides. It can be noise resilience, but also in a way take advantage of noise to actually improve performance in large-scale neuromorphic systems at scale, so both on the edge and in the cloud. But in this case, we can really go for efficiency and large-scale also at the edge. Right? And so to frame this, we all witnessed this this really amazing moment, and I still remember it. This was in fact, we had a meeting just at a conference, and I was we had this big announcement, and this tournament between the world champion and Google DeepMind, where DeepMind won. And this was a transformative moment, because for long we thought we will never in our lifetimes see this moment where the machine can beat a human at such a complex game, because high cognitive task. And ever since, so this was now about 10 years ago, so now it really has taken off quite exponentially from there on. So sure, we got the world champion in this game of Go being defeated by the machine. But also what is less known or less talked about is there is massive resource differences here. So sure, the champion lost, but it took 1,000 times more power of the machine to do it if you liberally account for, say, the entire metabolism of the human here trying to defeat the machine. So a factor of 1,000 if you count for all the TensorFlow processing units, all the hardware that was working hard to defeat the human here. So clearly, sure, we can get to performance, but what about efficiency of this natural or intelligent, this artificial intelligence? And if you observe the trends in deep learning, sure, we got really great advances in the accuracy of AI, seemingly to any accuracy that you want. We have this log scale advances over the years, but all those came at tremendous costs in terms of the amount of computation that is required to get those levels of performance. And in fact, the scaling is quite drastic, right? So for just a factor 10 in reducing the error rates, you have like 8 orders of magnitude increases in computational complexity of the amount of operation you have to do, and that translates then to equal orders of magnitude in energy. And so now we're getting to this astronomical energies required. So an entire right? So because lots of greenhouse effects, in fact, entire 1 month of the energy consumed in New York City, right, is consumed just for getting this task down to like 5% of an error. So that's so it doesn't scale. If you only go to 1%, it's going to be the entire world, right? So that doesn't scale. And so you can like attack this in two ways. Sure, you can reduce the number of operations required for learning, and that's extremely important. But there's also then the energy cost, right? So what is the per operation? How much you're actually consuming? And from there we can already make some advances that are very much inspired by how the brain is doing it. And this is very much closely related to also how, right? So, and I'll get to actually noise, because effectively what you have is you have noise in the system and you have energy, and those two are highly related through thermodynamics. In fact, right, if you look at the Landauer limit, that right, this tells you that in order to get a system that is precise, right, to just 1 bit, in this case, if you have this potential wells, right, so you want to hold, say, state in either one of two states here, right, bistable states, right, for this would be a bit in a memory, say, right. You want an energy barrier that is at least a KT, otherwise right, you'll be washing away. KT is basically your thermal, right? So your Boltzmann constant and thermal temperature, so that's your thermal energy. And so, yeah, you want your energy barrier to be at least that, right? So that thermal energy barrier to be at least, the barrier to be at least your thermal energy, otherwise basically you're washing away everything here, right? So that's the Landauer limit. And so that tells you for every bit that you want to store or compute, right, you need KT of energy as a barrier, which means for computing, you need to handle that barrier. So that's the limit, right? So that, and so there you can go down to really low power, like so 10 to the minus 21 joules, right, for each bit. And if you compare it with what they've been doing all along, right, with computing, so that's orders of magnitude, right? In fact, so that's more than 10 orders of magnitude difference here in digital computing efficiencies, right? And the brain is somewhere in the middle. So roughly speaking, so femtojoule per synaptic operation, which if you can derive that from, so about a 10 hertz spike rate on average. So each synapse, each of the 10 to the 15 synapses in the brain gets activated about every 10 hertz, so that together it's 10 to the 16 synaptic operations per second. And roughly speaking, you have about 10 watts of metabolic power in the brain. So the ratio of that gives you then a femtojoule per synaptic operation, or conversely, 10 to the 15 synaptic operations per watt of power, right? So that's somewhere in between in this log scale of efficiency, right? So how can we get, so that's about us, so the brain is pretty good. So how are we doing now with our digital hardware? Sure, you can say, sure, we have all these advances lately, right, with TPUs, stands for processing units, GPUs, right, graphical processing units, FPGAs, field programmable gate arrays. And sure, they're better, they're getting better. But most of the energy is actually consumed in exchanging basically memory, basically in exchanging data from processor to memory. This, right, and this transfer of memory is what costs entire power. It costs about 7 picojoule to get to a DRAM memory, right, for each bit. And so that amounts to, if you have 8 bits per memory, per weight for in a neural network, that gives you about 50 picojoule per multiply cumulate, because the multiply cumulate is all about getting the weight from memory, and then you do the multiplication, right? But you can only use it once. Caching doesn't help. All the stuff you hear about caching or weight reuse, it doesn't really apply for really large networks, such as the largest, large-scale language models they have now, right? This GPT-3 and etc. Right? So you can only use every weight just once. You can't really weight share. And so that's what, right? So you still have a massive amount. So basically you're limited by memory, and all you got in advanced memory has been a factor at most 10 or so, right? And in the faster, this HBM, which stands for high bounded memory. It's great, but still not quite. You still are shuffling back for data between the processor and memory at a cost, at a high cost. So computing memory is a way of bridging that gap, bringing the memory closer to the processing, or actually is the converse, bringing processing closer to the memory. In fact, you have an array of memory elements, and now you embed in each memory element the processor. So you do actually local computation right there for each memory element. And so then you really save tremendous amount of energy, because now the compute is right there at the memory. And so then you can get down to picojoules per multiply cumulate. And so now I show you our latest work, right, where we did this compute in memory using memistors, right, these arrays of conductive memory elements at femtojoules per multiply cumulate, and so they were closer to the human brain of performance. In fact, I will also tell you how we can even get better than the brain if you wanted to, by even recycling the energy that we have, right, of activating those memories here. So that's a landscape where we are. And again, so our fundamental limit is here. Can we get closer to it? Well, I'll make that statement now. Sure, we can even get closer to that, but we're going to be limited by noise, right? So if we can harness noise, sure, we can do this precise computation here, but so if we can get closer to this limit, right? If we can sacrifice some performance and so deal with resilient computing with noise, and that's really where COINFLIPS gets into, right? So, and I challenge everyone, so if you come up with algorithms in which you can deal with really imprecise elements, they can really bring down the power. And in principle, there's no reason why we can't get another factor 3 order of magnitude and get there. So that's basically an overview of what I'm telling today. Okay, so let me give just a very brief overview of what neuromorphic computing is. And most of you already know this, so I'll just go over this very quickly, right? But so over the last 30 years, a community of neuromorphic engineers has been doing all this in stealth mode. And only over the last 10 years, neuromorphic engineering has come to the forefront. But it's important to actually go back to the fundamentals of how Carver-Mead really formulated. And this is about the physics of computation, right? So where you really take inspiration from not only how neural systems compute, what they compute, but also how they are organized and their structural and organization and physical primitives by which they do the computation, which is very much rooted in fundamental thermodynamic limits of computation, which, right, so where you actually take advantage of noise rather than fight the noise, right, in the computation. And so then neuromorphic engineering takes inspiration from the structure and the physical foundations to build silicon integrated circuits that actually mimic directly the physics of the computation, right? With elements that are physically analogous to synapses and neurons in the brain. So that's basically, right, what we do in neuromorphic computing. And in fact, John von Neumann, even before Carver-Mead, really challenges all to think about the brain as a massively parallel computer that has noisy elements, right? In fact, it's very nicely put in his last opus here, right? The computer in the brain, right? He challenges to think of doing massively parallel computing with noisy, imprecise elements and still get resilience in large scale. In fact, everything we do now with neuromorphic computing, it was already in his book. So actually, it's really a nice jewel. And it's unfortunate because we keep talking about non-von Neumann computing. In fact, non-von Neumann computing was actually advertised in his book. And so to be fair, we should take the non out of the non-von Neumann computing because it really has been thinking about this 50 years ago. And so Richard Feynman also has given us great inspiration. So again, so Richard, so Dick has given us many things here, right? Carver-Mead as well. But so here's one thing that he put on his, Richard put on his blackboard, just before he died. What I cannot create, I do not understand, right? And so this is really pointing us to analysis by synthesis, right? If you really want to understand something, you have to physically recreate it, right? And he has been advocating for quantum computing, so actually build systems that can do it, right? But Asi has been telling us there's lots of room at the bottom, right? That's all great, right? But here's a very key realization, right? So if you really want to understand something, you have to actually build it. In fact, Carver and Richard had these meetings at Caltech where they actually thought about neuroscience and actually neurocomputation from physical principles. And And so Carver took this to an extreme, and I started this field of analog design neural systems, which he called then neuromorphic computing. And this is basically closing the gaps right between naturally engineered systems and the actual real neuroscience by taking advantage at each level of scale in the hierarchy, all the way from molecules all the way up to the mind of the brain, at each level of spatial scale and temporal scale, take advantage of physical isomorphisms, right, between the physics, the thermodynamics of what takes place in ion channels versus, right, because ion transport to ion transport through ion channels versus electron and hole transport through MOS transistors. And we have similar physics at play, even Boltzmann physics at the level of networks, right? Of networks, you can also model spin glass systems. In fact, that's what John Hopfield has been doing, right? He modeled spin glass system in neurobiology, right? And so we can now build this network. In fact, Boltzmann machines are extensions of Hopfield's recurrent neural networks that also take advantage of noise naturally present in the computing, right? For actually overcoming the energy barriers that you have in the spin glass systems, right? For then finding solutions to hard problems, right? Through effectively simulated annealing, right? So there's many great connections, physical, thermodynamic connections that you can make at the different levels of scale. And that's what neuromorphic computing is about, right? And so if you do that, so engineers can synthesize large networks from the ground up, right? Whereas now we can go close the loop for analysis, right? With computational system neuroscience, now we can actually study large systems emulating the brain at scale, and now let neuroscientists, right, then validate, right? So basically validate hypotheses, right, that we make up here, right, in neuroscience. And this way you can close the loop. And that's what systems, computational system neuroscience and neuromorphic system engineering are bringing together as synergies, right? So, so I already mentioned Carver-Mead had this realization of this physical isomorphisms of subthreshold analog circuits, right, that have some similar exponential relationship between conductance and membrane, in this case, gate voltage, right, membrane voltage, right? Transistors will have similar conductance profile, exponential conductance profile, as those ion channels in biology, right? And so that gives you an exponential range, the high dynamic range of conductance that with just small voltage differences that we can accomplish. And that's all you need to really do very precise, or actually high dynamic range computing, taking advantage of orders of magnitude of dynamic range at very low power, because now you're talking about femtoamps to picoamps to at most nanoamps of currents that you have here in this range. So this subthreshold metal oxide semiconductor MOS field effect transistor FET domain of operation is where most of neuromorphic computing operates, and that's where you can get really high dynamic range for doing things like silicon retinas, right, where you can have large orders of magnitude of range in intensity of light that can be transduced with these elements here, right? There's photoreceptors, and then you have other circuits implementing different layers here, right, of retina, including then the retinal ganglion cells that model then this both sustained and transient spike responses to visual input. And so, sure enough, we can then model the world with spikes, right? And the spikes is being done here, right? You have this on and off events that can code what is happening here. The temporal and spatial effects or events that happen on the focal plane are then coded with spike events, right? And that's then communicated over the optic nerve, the rest of the visual system. And it's amazing what you can just do with spikes. You can actually reconstruct your visual scene just purely from the spikes here. And we all know that because from our brains, we know that we can just the optic nerve carries everything we see, right, with just a few 100,000 fibers each, with about 100 hertz of of spike activity. So it's just like 10 or a few tens of megabits, mega events per second is all it takes to capture the entire complexity of the world that we see, right? So there's massive compression that takes place there. And so you can do some further compression, right, in temporal domain here. In fact, you can implement vision sensors. We call this dynamic vision sensors that purely encode temporal change events on the focal plane. And this way you do great compression. Only when something actually happens, right? There's a temporal event that happens in the pixel, you actually send an event, in this case, a +1 for the rise in intensity or a -1 for a fall in intensity. And that's, again, enough for reconstruct your scene and do some recompression, right, for surveillance applications. Right, so, and so those are sensors. And then now, so going into Cortex, now you can take advantage of those spike-based, event-based representations for doing computing. And neuromorphic computing over the last 20, 25 years has taken advantage of this event representation, this event-driven representation, so basically address event representation, right, spikes, right, and their addresses to really then code and networks, so encode networks and implement large range connectivity, reconfigurable synaptic connectivity and plasticity in those networks of this chips that where the wiring between the synaptic wiring between neurons are taken care of by basically lookup tables in memory, right? And so that's the field of neuromorphic computing. So why is this actually important, and what can we get here at large scale? And so I mentioned in my talk is going to be at the edge. And that would suggest very small scales, but still we want to get really amazing complexities, and so even just like if a fly visual system has massive complexity that you have to account for. In fact, not any less complexity to navigate in complex scenes, right? What the fly is doing, than the complexity, say, of solving the game of Go. So we have a wide range of task complexities. And we have to deal with that with massive machine complexities. So human level, right, of intelligence, right, would be on the scale of really hard tasks here, right? And so there we can deal with about 10 or 15 synaptic operations per second. And sure enough, so the best you can do is to have that complexity that you can account for. Now, what neuromorphic computing does, as opposed to classical AI, is rather than trading a task complexity for machine complexity with parity, if you want to look for an exact answer to your problem, you basically need to go through the entire state space and search, right? So that basically your search will incur a complexity that is at least, right, as complex as the task at hand. And so that was basically a linear trade-off, and that doesn't scale, of course, at large system. So what deep learning does, right, is abstracting from the complex world lower dimensional representations, and neuromorphic systems do the same, right? So basically, so analog collective computation, you can think of it really as an effect of deep learning. You look for patterns in the world that are as opposed to this crisp digital search task, right, or the search strategies. You look for analog, right, so for basically networks of distributed representations, right, neural networks. And then so with deep learning, you can find these lower dimensional representations that then capture your world, right, with reduced complexity. And neuromorphic computing can do this now at great efficiency. Ideally, you want to get at the level of, right, so for the human brain, 10 or 15 synaptic operations per second at about 10 watts of power. That's what we want to get at, right? And so to get there at this efficiency, it's important to then think of complexity or energy, right, in terms of decomposes in two important factors. One is energy per operation, and the other is operations per task. And we want to minimize both, right? And so neuromorphic engineering will be concerned about mostly lowering the energy operation by doing this really efficient compute in memory architectures where you bring memory close to compute. And this way you can get down to femtojoules per synthetic operation versus the tens of picojoules per multiply cumulate that we have, say, with those GPU/FPGA, etc., right, systems. And then you can also minimize operations per task by doing deep learning, and also I would say neuromorphic deep learning, which would be stochastic resonance kind of ways of doing your learning with Boltzmann and other machines, right? And I'll say a few words about this as well. So those are two important aspects. There is the device level optimizations, right? Bringing, basically lowering the operation, the energy per operation. And then there is the algorithmic optimizations where you want to lower operations per task, right? And so you want to do both of them. So I'll just, I will emphasize some aspects of each of those two, focusing on how all this energy also relates to noise, right? So energy and noise are very much related. And so I'll mention both of this now. Okay, so let's start with mostly this ways of really getting high efficiency and high density, right? And so here is a state of the art of other large-scale reconfigurable neuromorphic computing. So those are all systems that embed this Addis event representation, right? So that can do this arbitrary network interconnectivity between neurons and synapses by basically having those event-based representations for coding synapses, right? And then this way can build in principle any network. And so here shown are then the efficiencies for large, these are mostly large networks. It's not complete by now, we have some other very nice systems that are there, but just still, if you look at efficiencies, right? So still IBM True North still has gotten the greatest efficiencies in terms of and densities, right? So 1 million neurons and about 256 million synapses, all integrated in one chip, right? With about 26 picojoule per synaptic operation of energy. And other systems also give, have comparable efficiency, and I just note here both digital as well as analog systems is about a few tens of picojoules, and most of that is limited by access to memory, right? And if you could bring the memory closer to the compute, of course you can do better, right? But this is basically tens of picojoules of energy per synaptic operation, and that's where we are today, right? Or maybe 10 years ago. And in order to get to large scale, it's important to get both, right? So I mentioned reconfigurable connectivity. What you want is both long range. You only be able to connect from one side of the brain to the other side of the brain with just a few hops in a hierarchy of interconnectivity. And that's the white matter. So with the white matter of the brain, you want to be able to have just a few hops in a small world network, right? And so there, tree-based networks will give you the greatest efficiency, right? You have some hubs, right, where you can get to really, you can make big jumps, right, spatially. And then you have, so as you dive down in hierarchy, you have you have lots of local nodes in your network, right, that are distributed. And then you have a few hubs that can really range over the entire network. And so in the brain, indeed, you have two hemispheres, right? Each hemisphere, right, has this large fiber bundle, this axonal pathways between them, the white matter that connects those two hemispheres, right, with great density. And yet these diverse parts, because clearly not every neuron connects from one hemisphere to the other hemisphere, right? Think of that, the superhighway that you have between the two hemispheres, it's limited, but it's important, right? And so then here you have, say, your other regions of the brain, and then down there, eventually you have the microcolumns, right? So the white matter gets you there, right? In this hierarchical interconnect. And then the gray matter is how you can implement arbitrary connectivity, right? You can still, each neuron can still connect to many other neurons, and there's the synapses, the local synapses, the gray matter that implements this fabric. And you want this to be arbitrary with high density interconnect. So right there, if you want to implement a large neuromorphic system, you want to get both the white matter implemented as a very efficient, almost an Ethernet, right, of event-driven communication for the white matter across large scales. And then you have local interconnects, right, ideally with computing memory for doing this high density local connections for implementing the synapses, interconnecting neurons locally, right? And that's what higher does. Hierarchical additive and routing gives you both tree-based interconnect as well as flexible local interconnect, right? So high density local and low density global, but hierarchically structured wide range connectivity is what hierarchical additive and routing gives us. Right? And so what it does in practice, that basically means you have local processors that can take care of your identifier and other dendritic computation, right? And all this is analog, so with inherent noise. In fact, you have natural noise presence in your dendrites and the soma. That's an important aspect of the computation. And so you can think of those as this integrated fire array transceivers, right, where you have spikes that come in to this array of neurons and implement the synapses. And then when a neuron spikes, then an event is going out of the system and that's communicated to the periphery. And so now you have events in and events out that are digital. So the system is basically an entire external digital system, but internally analog, right? Implement all the neurons. And external to that, you have now a processor with memory handling each event. So for each output event, so basically now you go in your table, and that's now it's going to be presynaptic to other events, right? So you have presynaptic addresses in the table that you write for the neuron. And now you find postsynaptic destinations in the table, in the data field of the memory, as well as with their parameters, right? And so basically you circle to the memory, and that's how you implement basically any arbitrary network by basically reprogramming the memory, right? Both the connectivity, basically postsynaptic identities, the addresses, as well as the data, the actual strength of the synapses is encoded in memory, right? And so you can, in principle, just build any network that way. And so that's how we implemented basically. So that's done for local interconnect. You have this local processor doing that. And then for long range interconnect, and basically you have events that can also pass through the hierarchy to other processors, right? Other boards, other nodes in the right, other supercomputer centers. And this is a way how you can basically build large scale networks, right? With almost constant density of traffic, right? Because at any level of scale. So that was higher, we call this higher IFAT. And so there we got about 22 picojoule per event of efficiency, mostly limited by this interconnect of the memory, right? Having to go to this memory. We have some other versions actually where we put the memory directly next to high bounded memory, right? So directly you have high bounded memory interfacing with our processor for doing that more efficiently. But still we're limited by basically DRAM access, right? Whereas high bounded memory, it's still DRAM, right? In this case, and so that's an order of tens of picojoules per spike event. Now, can we do better? Sure, you can bring the compute close to the memory because what are those memories? Memories are basically banks of elements where you store a bit of memory as at a voltage or something else. Now, non-volatile memories, and those are basically your EEPROMs or your flash memories, and nowadays those are now your PC RAM or some other emerging memory technologies. So those memories actually store, right, information as conductance as opposed to some voltage that you store somewhere in a DRAM, right? In this case, what is stored is basically conductance. So either it's, right, so yeah, and in fact, that conductance is analog. For phase-change memory, there's an analog conductance that this element stores. So normally what you do for memory, you select, right, the word line, all right, so you get an entire bank now of the memory. So now the bit lines will give you that bank of memory going out. And so you can get sequential digital access to this memory by basically selecting, right? Basically by decoding your address that selects the word line, and then you can get an entire parallel output of your memory elements coming out, right? So that's a digital way of doing it. But now, in a neuromorphic system, an actual synapse is actually really the same thing. You can think of a synapse as a conductance. In fact, what is a conductance? A conductance is actually what is a synapse? It's a postsynaptic conductance, right? That gets activated by a presynaptic action potential. So think now of the word line being driven by presynaptic action potentials, and now you activate a conductance, a postsynaptic conductance between your output, your membrane, your dendrite, and then here's your reverse potential, right? You can say your reverse potential. So there's as biophysical of a synapse as it gets, right? And so that's for every bit in a memory that you normally have in your PC RAM, you actually now have an analog synapse, right? And more than that, it does a compute, because when you drive this word line with your presynaptic action potential, you actually get, you aggregate, you get your currents directly into your dendrite, in the dendritic tree, and that's all you need to do, right? And so, in fact, Intel Micron's crosspoint technology can do that. In fact, if we just had, if we could get access to that, it would be wonderful. In fact, what we have access to is in addition to phase change memory, right? We have access to some other technology, but so, right? So you could have crossbar arrays of those now with, so you have inputs that go in one direction and outputs that go in the other direction. So presynaptic, right? Presynaptic action potentials will be driven, say, let's say, for instance, here, along the bottom lines here, let's say horizontal, and then you accumulate currents in the perpendicular lines, in this case vertical lines, the postsynaptic terminals, right? And this is purely conductance is activated here, so that's directly you can do here. So with simply by, and so this is a totally parallel operation. So in one clock cycle, you can implement an entire array of those, right? So we have action potentials being activated, right, in an entire network, let's say 256 neurons, and then you can observe those postsynaptic membrane potentials, right, for 256 output neurons if you have a 256 by 256 array of those, right? So you get massively parallel compute in just an array of synapses, right? So this we call a crossbar array of synapses, and you may have already heard. So when we talk about a memristor array, that's basically a crossbar array of synapses, right? But now what we can do is we can directly connect that array of synapses with CMOS neurons underneath of, right? And so what we have is an array of those, this integrated fire array, integrated fire neurons. So this is our integrated fire array transceiver array. This is an IFAT array that we had here, right? So the same IFAT that we had up here is now implemented here, right, with an array of these neurons underneath your synapses. And so you have the address event inputs and outputs to this array. They can take care now of long-range connectivity. That's your higher, Harker's address event routing. And then locally, you already have your local synapses, right? The gray matter is right there because each neuron can reconnect to the synapses locally, implement this full connectivity locally, right? And so this way, now we can implement this very large, this was now implemented with resistive random access memory, which is similar to this phase shift memory. It just is a different mechanism. In fact, those are called memristors, right? But this can be done in CMOS. In fact, we embedded that in our CMOS technology. So we had layers of RAM on top of the CMOS that implement this this metal oxide, implementing this variable connectivity implemented here by basically this RAM, this resistive random access memory. And then in CMOS, we have this array of neurons that are embedded, right? So we have this array of 16 by 16 array of neurons, right? And those are the blue here. Those are neurons that we have in, and then we have an array of 256 by 256 synapses. So we have 65,000 synapses. Basically, we have 256 rows and 256 columns as a crossbar arrays on top of the CMOS, right? Those are your synapses. And so then we have this reconfigurable, or in fact, this reconfigurable data flow, right? We can, right? So each neuron can connect to either a column or a row in the architecture, right? So for driving this neuron input, as well as collecting, right? So basically, the presynaptic can either be a column or a row, and the postsynaptic accumulation, basically the membrane, the dendrite of the neuron, can either be a row or a column. And you choose, right, whether you connect the row or the column, and this way you can actually implement inputs vertically and outputs horizontally. That basically means the input goes in on the bottom and comes out on the right, or the other direction. Now you can come in, right, on the right, and the output goes in the bottom. So this way you can actually reflow the direction, right, so you can redirect the flow to the network. And that's important if you want to go back through layers, right? You can do back propagation to your layers, or when you have a Boltzmann machine, you can go back and forth between hidden and visible units, right? Basically by doing inference and generation, right? This is going back and forth. And that's extremely important because now for stochastic system, this going back and forth is exactly what you need. Gibbs sampling is very important, right? For basically making inference in those networks of stochastic neurons that you have, say, for a Boltzmann machine. Okay? And so we do this at great efficiency, in fact, by bringing the memory very close to the compute, and in fact, also having very efficient neurons, and I'll leave you the details in this paper, right? We're able to bring down the compute energy down to just femtojoules per kinetic operation. So now we get almost basically 70 teramax per watt, or 13 femtojoules per kinetic operation, which is higher than, at least twice higher than the best computing memory systems that have been implemented with this technology. So that gives us really great efficiency. So now let me actually get down to some computational aspects. We can do this stochastic inference, right, with Boltzmann machines, basically iterating between, with Boltzmann machines, you have visible units and then you have hidden units, right? The visible units are the pixels that you have. The hidden units are basically the neurons that represent different concepts. In this case, you could think of different digits, right? Digits you recognize. And so you can go back and forth. For inference, right, you get the inputs, and now you want your neurons to classify. But for generation, you can go the other direction. So you can actually ask any neuron, okay, generate, so neuron 6, generate me a 6, and it will generate an actually 6 on the fly, right? And it does that by basically injecting noise in the system, basically dreaming up by injecting noise in the system as a Boltzmann machine, right? You can actually generate the 6, right? And so, and this going back and forth between inference and generation is extremely important for the latest generations of learning, right? So restricted Boltzmann machines is one, but also variational autoencoders, exactly the same thing. And that's actually, so all the great stuff you do now with variational autoencoders, but also GANs, right? So generative, right? So basically you have generative models that are adversarial, right? Generative adversarial networks, right? They can actually dream up the world, and so this allows you to really learn much more efficiently. In fact, you can do some amazing things with GANs or generative adversarial networks. Okay, so the point here is that we do this at great efficiency, and so here's a demonstration of that, right? So here's so you give a network a 6. You obscure pixels, right? So that's, you add noise to the system, and now that the system actually classification, it gives you a 6, but more than that, it actually cleans up the noise, right? It actually cleans up the noise in the system, right? And that's your inference as well as generation, right? So you recognize a 6 and also generate it. And it does this now at energy that is much lower than what you do it on a digital computer. This was, by the way, this was a real demonstration, a recorded demonstration of the chip in operation here. This is all hardware and implemented in silicon. And so we took this one step further. So now, so that's one demonstration for one core. Now we have an array of cores. In this case, we have 48 cores of this RM CMOS array with 3 million RM cells, so up to 3 million synapses, and so several tens of thousands of neurons, right? And so each core is one core that does this local dense interconnect, right, with crossbar array. And then we can have higher that interconnect between all those cores. And now you can implement any network by basically mapping the network onto this system. And we have done different types of networks, CNNs, right, convolutional neural networks, recurrent neural networks, LSTMs, right, long short-term memories, etc., for different tasks, right? And we're able to demonstrate on this network not only great efficiency, right, similar efficiencies as reported in the other paper, right, femtojoules range, right, but also really great performance on all the different tasks. We're able to map different tasks on the system by basically reconfiguring the architecture, right, remapping the architecture in the layers on this different cores in the architecture, and taking advantage of this going back and forth between layers, and we're able to bring down the performance, the error, down to levels that are comparable to that of digital implementations by basically chip in the loop training, right? Just going over the architecture, basically you can map this architecture, right, onto this in the different cores, right, in this architecture, right, and then we're able to actually retain. So basically, what we did in chip in the loop training, basically we trained one layer at a time, right, in software. Then we program the weights, right, for that layer onto the hardware, and then we observe the output on your training set, right, at the output of this first layer, and now train the rest of the network from that, starting from that layer, right, in software. Again, now figure out, right, so again, learning the next layers in network, right, again with the task. And so basically this way we learn one layer at a time. And sure enough, by basically taking advantage, so basically now what the system will take into account the errors that were introduced by the hardware, right, in the first layer after programming it, and then we'll retrain based on those errors, right? We'll retrain the next layers and accommodate for the error, exploiting the basically the what you have available in next layers, right? The complexity available in next layers, and that's and in the process we inject the same noise. We inject the same noise, right? That is naturally present during the inference in the training process, right? And there's whereas the Boltzmann machine, you definitely do that, right? You inject noise. Even when you're doing classification network like a CNN or an RN, you still inject noise in the process for doing whether it's drop connect or drop out, right? So basically you implement by injecting noise in the system, right? You generalize better. And so you can actually take advantage of the physical noise that is present during inference anyway, to actually also model the training and have the same noise present during the training. And so this way, we're able to actually bring the performance up to almost the same level as the digital hardware, right? And this was a Nature paper that we published this was last August, and so this is open source, open access. You can all access that paper, so more generally, right? You can do this learning, taking stochastic processing into consideration. In fact, you can even model stochastic synapses, and that's work with it with Emre Neftsi many years ago, now 5 years or 6 years ago. Where we actually be able to actually learn, take advantage of stochasticity in the synapses, right? In actually getting very close to the digital performance and at a much greater efficiency than, right, of your compute. Okay, so I think that's, I'll wrap up in a few minutes here, but so we can go one step further even, right? So you can even get greater efficiencies, and just, I mentioned in the beginning, so how far can we go? If you can recover, if you can recycle the energy that you actually use for compute, then you can even get better performance. In this case, if you have charged the main elements and even recover the energy for driving those lines capacitively by coupling that energy, capacitive energy, right, with inductor, an external inductor, basically you can cycle that electrostatic energy as inductive energy, then you can actually recover all the energy it takes for computing. And this way we're able to get at resonance, right, of the system, where the compute of that you have in this charge domain elements is at resonance with the external coil, right? We're able to actually recover about more than 90% of the energy. And this way we're able to bring down the efficiencies, right? Bring up the efficiencies to 10 to the 15 centimeter operation per second at 15 watts, right? And same to that of human, right? So basically a femtojoule per multiply cumulate, right? And now and so we can even get a factor 100 better in latest technologies, and that's work we have now on the test bench, and we're testing that now. So those numbers are simulated, but now we can think we can get up down to about 100 attojoules, so at least 10 times better than the human brain. So that's where we're now. And so again, stochastic resonance is important here. And so how far can you get? You can even push it. So I think we will be able to eventually get down to the Landauer limit, and that would be another factor 2, so it'll be about 5 orders of magnitude better than the human brain. If you really harness then stochastic computing all the way at the atom level, it will be possible. I'll leave that algorithmically to you. And then, so we'll also keep working on neuromorphic circuits that can actually get closer to doing resilient computing, right, at fundamental limits of energy efficiency. So we have also built some hardware that does basically digital hardware for large-scale systems, not efficient, but at least very reconfigurable, all the way up to 160 million neurons and 40 billion synapses, and that's open to the community. I can point you to the workshop that we had at Telluride. We still have our system now available for people that can play with that hardware. You can send your job description, Python description of a network you want to emulate, and then so we'll emulate it with up to 160 million neurons and 40 billion synapses on this system in real time. I will just skip this. So you can also close the loop, right? So in fact, there are also some other, at each level of scale, there are also some brain-computer interfaces, right? All the way from uninvasive EEG down to the very invasive molecular probes that can further extend this neuromorphic systems down to each level. So in this way, you can have brain-computer interfaces at all levels of scale, right? For really closing the loop, right? For at very great efficiency for, say, probing function of the brain, and actually that's for augmented cognition and also for remediating neurological disorders. But I'll leave it there. And so basically we can close the loop here. And so what I mentioned here, so yes, we can get great efficiency in neuromorphic computing, but also then we can take advantage of that efficiencies, right, to also interface with the brain at large scale. In fact, I can just leave it here, right? So we can take advantage of all that. And so noise is very important. So learning and adaptation is important, but noise is extremely important. And actually my postulate is that we'll be able to get this efficiency of the systems, right, even up, because beyond that of the brain, if you do things carefully, and get there with getting close to thermodynamic limits of noise energy efficiency. And with that, I'll just have maybe a few minutes for questions. I have not heard any questions, so please, yes.
Thank you so much. That was fantastic. We've got some virtual applause going through. While the audience takes time to think of a question, please do raise your hand and you can ask away. But while